Hello friends, I welcome you all on India's largest live e-learning educational platform, that is Gradeup. Friends, today we are going to discuss some of the important concepts related to the transformer. In the previous class, we have discussed some of the basic construction details and we have discussed some of the concepts related to self-inductance, mutual inductance, leakage inductance, all those things we have discussed. Now today we will be discussing some of the topics. All of you who are joining me here, please tell me whether my audio and visual quality is okay for you so that we can proceed for the session. Till that time, I am just listing out what are the topics we are going to cover today. Please tell me quickly whether my audio and visual quality is okay for you so that we can proceed for the session. So these are the list of topics we are going to cover today. Let me just write it down so that you have an exact idea what we are going to cover today. Transformer action we will be covering first. EMF equation for primary and secondary side. Hello Surya, how are you? Good evening. So I am audible. Next we are going to see the ideal and practical transformer. Then we will see MMF balance equation. Then we will see voltage regulation. And then we will see efficiency of the transformer. Is it clear to all of you? So the first slide on your screen shows how to wash your hands so as to protect yourself and others against the infections related to the novel coronavirus. This is the initiative started by Team Gradeup as hashtag Prep Smart Stay Safe. As you can see on your screen, the steps to properly wash your hands are: you should wash your hands under the direct tap water, apply soap, rub hands palm to palm, lather the backs of your hands, scrub between your fingers, rub the backs of the fingers on the opposing palms, clean thumbs, wash fingernail, fingertips, then wash your hands under the direct tap water, dry it using a towel and switch off the tap by using a tissue paper or the towel, and now your hands are clean. This procedure should approximately take 20 seconds as per the government regulations. Yes, Surya, thank you so much for your concern. I am completely safe and I hope that you all are safe staying in your home. Good evening, Pandari, how are you? Now the next slide shows the contact number for the control room which is being set up at the national level to address the queries related to the novel coronavirus. You may reach this number for any guidance, support and technical queries. This also we are communicating under the initiative hashtag Prep Smart Stay Safe as started by Team Gradeup. Now before we start the session, there is some important information I want to give you, that in this time when everybody is restricted to stay in their home, the moment this lockdown is going to be over, everybody is going to be oriented towards their examination. But don't waste this time. So Gradeup is offering to you to best utilize your time when you are staying in your home. That is the Gradeup free classes on the Gradeup classroom. M.N. Ramesh sir, Chandan Jha sir, Rakesh Chaleja sir, they are taking engineering services mains practice class 9 a.m. in the morning. Chandan sir is taking concept on fingertips classes at 12 p.m. I am taking engineering ethics classes for engineering services 2021 paper 1 at 1 p.m. Monday to Friday. Vijay Bansal sir is taking concept on fingertips classes at 2 p.m. and again M.N. Ramesh sir is taking concept on fingertips classes at 7 p.m. daily. Now there is some important information regarding this Target Gate 2021 batch that we have just started. It is an electrical engineering course. The most important feature is it is going to be a bilingual course. So इसमें हिंदी और इंग्लिश दोनों में बातचीत होगी, so that language is no more a barrier for your learning. The faculties which are going to take classes in this batch is Rakesh Talreja sir. He is ME IC Bangalore AIR 9 10 plus years of experience. Myself Ashutosh Saxena M.Tech IIT B.H.U 10 plus years of experience. MN Ramesh sir ME Osmania University Hyderabad 17 plus years of experience. Vijay Bansal sir 19 plus years of experience. Chandan Jha sir M.Tech NIT Hamirpur 9 plus years of experience. Thousands of students have started the free trial, let me tell you, and you all should at least start the free trial even if you are not interested in this. Thank you so much, Baliram, for your appreciation. Now, all of you, I am going to start the transformer action now. But before this, let me tell you that if you want these classes to be available for you, don't forget to like this page and share this video in your friends circle or the social media group so that maximum people can join it, because it is a kind of feedback we get from the students. So this motivates us to keep on making such videos. So don't forget to like this page. All of you just quickly like the session. I can see very less number of likes are there. Quickly increase the number of likes, all of you. Okay. Now first we have to understand what is transformer action. Okay, for that purpose you just listen to me for a moment and then we will understand what is transformer action. Suppose this is switch S1 and this is switch S2. This is some AC supply. All of you must be very clear in your mind that we are going to use the transformers only with the AC supply. We are not going to use the transformer for the DC supply. I hope you may be knowing the reason. Now please try to understand, if you are providing an AC supply here and suppose at some time you close this switch at t is equal to 0. Listen to me very properly. Very interesting phenomena is going to happen here. The moment you close this switch S1, so when S1 is closed, what is going to happen? Because this circuit is complete, there is going to be some current here. Let it be I1. Yes or no? There is going to be some current here, I1. And this I1 is going to flow through this primary winding in this direction sense. And suppose there are N1 number of turns in the primary side and there are N2 number of turns in the secondary side. Now this current I1 circulating through this coil, it will give rise an MMF which is N1 I1. Yes or no? Are you getting this? Now this switch is not closed. This switch is open. It is open. So it is the open circuit, or you can say no load condition. Whenever there is a load, you will always characterize load in terms of current. So when we are saying no load, it means the secondary current is going to be 0 and there is some primary current, and this primary current we are calling as, this I1 is going to be equal to I naught, which we are calling as I naught as the no load primary current. I hope it is visible to you. No load primary current. Okay. Now please try to understand. This MMF is going to give rise to set up a flux in this core. We have read it in the magnetic circuits. So there is going to be some flux set up in this core which we are calling as phi. I hope it is clear, and the direction of flux is You can find by using the right hand rule. What is the right hand rule? You close your right hand fingers, curved fingers, in the direction sense of the current, and the direction of thumb is going to give you the direction of flux. Baliram, beta, please, if you are not interested, let me make it very clear. If you are not interested in the class, you can leave. This class is only meant for those students who are interested in what are the topics we are going to cover. Don't waste your time and our time. Okay? So just focus here. Now what is happening? First thing is S1 closed, MMF is set up, and this MMF is going to give rise to a flux phi. Yes or no? Now this flux phi in case of a transformer is a time varying flux. Yes or no? This is a time varying flux. Now when this flux is time varying, it means this flux linked with primary winding is changing with respect to time. Then because of the Faraday's law, some EMF is going to be generated. Yes or no? An EMF is generated in the primary winding as per Faraday's law. Yes or no? Now suppose the EMF which is going to be induced here is E1, and we don't know what is going to be the polarity of this induced EMF. Now I'm going to tell you very important concept, how to figure out the polarity of the induced EMF in case of a transformer action. Now suppose at any point of time for this AC supply, this terminal is positive and this terminal is negative. Now please try to understand how you are going to find the polarity of this induced EMF E1. Now I am saying this, I will write this and you understand it. The polarity of induced EMF E1 would be such that if given an opportunity, it will circulate the current in the direction to oppose this change in flux. I am saying it again. The polarity of induced EMF E1 is going to be that polarity that given an opportunity to circulate its own current, it will circulate the current in the direction so as to oppose this change in flux. I hope you are getting this. So how you are going to write this? Polarity of E1. Given an opportunity to flow its own current just G.V. Raju, Lenz's law, the E1 would circulate the current in a direction so as to oppose the change in flux phi t. This is very important and this is as per the Lenz's law. I hope you are getting this. Now let us go back and see. Suppose this source is not there. You connect some load here. So what is going to happen? E1 is going to make the current flow in which direction? In the direction opposite to the direction which is the direction of I1. So this is going to be plus polarity and this is going to be minus polarity, because it wants to circulate the current opposite to I1. It wants to oppose the cause. What is the cause? The cause is I1. I hope you are getting this. All of you, please tell me. Yes, all of you, Sanjay, Bonsu, all of you, please tell me, are you comfortable with this polarity of E1 induced in the primary winding? Are you comfortable with this or not? Please tell me yes or no in the comment section. Are you getting this? So that we can proceed. This is very important in GATE examination. Very easy and direct questions can be asked. The only criteria is you should know how to decide the polarity. Please tell me quickly yes or no in the comment section so that I can proceed, because this is very important to understand further concepts. Okay. Now see what is happening. This flux is again linking to this secondary winding. Yes or no? And because this flux is time varying, this flux is also going to induce some EMF here also. Suppose this is E2. Yes or no? And how you are going to write? Phi t linked with secondary winding will induce an EMF E2 as secondary is open circuited. Now please try to understand. This secondary circuit is open. This switch is open. If this switch is open, no current is going to flow, but still there will be some EMF. What is that EMF? E2. Now how you are again going to find the polarity of E2? The same logic you will apply to find the polarity of E2 also. What is that logic? That logic is, given an opportunity, E2 will flow the current in such a direction so as to oppose the change in flux. Yes or no? Again Lenz's law. Now please try to understand. Right now this switch is open. We are not concerned with the polarity right now, at least right now. But the moment this switch is closed, we will try to see what is going to happen. Okay. Okay, now let us see the polarity also. Suppose if you want to see the polarity E2 here, the moment you close this switch, in which direction it is going to flow the current? Just see here. The direction of the core flux is this direction. And if you want to oppose this flux, then you should have some flux generated by this current in the secondary winding in the upside direction, bottom to up. Yes or no? Apply the right hand rule. What should be the direction of current? The direction of current is going to be this direction. Yes or no? Are you getting this? So definitely E2 is going to be having this polarity. I hope you are comfortable with this understanding. Ranjit Mahal beta, अगर नहीं समझ में आए तो पूछो. If you are not getting it, then you can ask me n number of times. No problem. You ask me exactly what is your doubt. Now, transformer action, the actual reality is going to come. Now, please try to understand what is going to happen. Suppose this switch is already closed. This S1 switch is already closed condition. Now, suppose you close this secondary side switch at t is equal to 0. What is going to happen? Please listen to me. This is very important. When this switch was closed, the current in the primary winding was like this. And because of this current, there was MMF because of the current in the primary winding. And it is going to set up a flux like this. And the direction of this flux is going to be this direction. Yes or no? Now please try to understand, the moment you close this switch, some current is going to flow in this direction, which we are calling as I2. that is the current in the secondary winding, and this is having N1 turns and this is having N2 turns. But again, as the current flows in this direction, there is going to be some MMF which is going to oppose this flux. Yes or no? Yes or no? This MMF N2I2, this N2I2 is going to be opposition to the flux set up by this N1I1. So definitely the flux has to be reduced. What is happening? When S2 is closed, I2 flows in the secondary winding. Yes or no? I2 flows. Yes, I can explain n number of times, Sanjay beta. You tell me what is your exact doubt. I will tell you 100 times. Now the MMF, that is the secondary MMF, opposes flux phi 1. So phi should reduce. But let me tell you very important point, and that point is, I am writing it here. Phi cannot change as its source is supply, because your AC supply is going to establish this flux cannot be reduced, and if this flux cannot be reduced, what is going to happen? I am just removing my photograph so that you can see the content on the screen. The reduction in flux will be compensated by drawing some extra current from the source. Okay, Sanjay, definitely I will tell you, but first of all, you tell me whether you are getting this idea or not. You just understand it, try to understand it, otherwise I am going to repeat it. This we are calling as the transformer action. How we are defining the transformer action? Please listen to me. We are writing the transformer action like this. The load connected at the secondary terminal is being supplied by the source connected at the primary winding. GB Raju is asking, sir, why flux is going to be constant when load is connected? Beta GB Raju, you listen to me. Listen to me. I am just writing one statement and you will tell me what is the answer. Inductive coils does not allow sudden change in current. Yes or no? You must be knowing this. This is very basic thing in case of your networks. Inductive coils are not going to allow the sudden change in the current, and the capacitors are not going to allow the sudden change in the voltage. Can you tell me what is the reason why they are not allowing? Because your inductive coil is going to have a flux linked with it. And if you suddenly change the current, the flux is going to be changed suddenly, which is not possible. So because your transformer primary and secondary coils are nothing but inductive coils, the moment you close switch S2, there is going to be some current being flown in the secondary winding, and this MMF N2 I2 is going to oppose this flux phi, but phi is not going to change. Why? Because who is going to establish this flux? Supply. If supply is not changed, how you can change the flux? It means at the end of the day, the load which you are connecting, it is going to be taken care by the supply only. This phenomena of connecting the load at the secondary side, and the load is being supplied by the source connected at the primary winding, this phenomena we are calling as the transformer action. All of you please tell me whether you are comfortable with this understanding of transformer action or not. Because if you don't understand this, then even if you do the numericals, you are not going to understand the transformer properly. All of you please tell me quickly, are you comfortable with this? Then I am going to take up the doubts by Saran Kumar. I have just said that the inductive coil does not allow the sudden change in current. Why? Because flux is linked with these coils. If you see the case of the capacitor, why capacitor is not allowing the sudden change in the voltage? Because there is some stored charge. That is, stored charge is nothing but electric flux. This phi is the magnetic flux. In case of capacitor, it is electric flux. This is the reason. And the second important thing is that this flux is being set up by the supply at the primary side. If the supply is not changed, how you are going to change this flux? It means there has to be some change in the supply side. Now what is that change? That change is extra current drawn from the supply to meet the load which is connected at the load end. I hope Saran Kumar it is okay. Now all of you listen to me very properly. I am going to tell you very important concept regarding the transformer. Please listen to me very properly. When there was a no load condition, I am writing it here so that you can see it. Just listen to me. In case of no load condition, at the primary winding, what was the MMF? That MMF was N1 I0. What was I0? I0 was the no load current. No load current at the primary side. Yes or no? I hope you are getting this. In case of on load condition, what is the MMF at the primary side? This is going to be N1 I0 plus some current. This current I am calling as Ix. This is the extra current. This is the extra current which is drawn from the source. Yes or no? Are you getting this idea or not? And at the secondary side, what is the MMF? That MMF was N2 I2. This is the primary side, and this is the secondary side in case of load condition. And what is transformer action? You tell me. Transformer action is that the MMF, because of the current in the secondary winding, is going to be compensated by extra current drawn from the primary circuit, the supply connected to the primary circuit. It means this N1Ix is going to be equal to N2I2. Are you getting this idea or not? Then Ix is going to be N2 upon N1 and this is going to be I2. Ranjit Mahal, beta, if you have any doubt, I am requesting you, it is my humble request that you ask your doubt in a proper way. You ask your doubt, writing your exact doubt in the comment section. Otherwise, it is not possible for me to take up your doubt if you write it half-heartedly. Now just listen to me very properly. Okay. Suppose we are calling the transformation ratio A as N1 upon N2. Can you tell me what is this current? This current is going to be I2 upon A, and this we are calling as I2 dash. What is this current? You listen to me very properly. If you understand this, then the whole rest of the transformer theory is very easy. That is only maths. This is electrical engineering. This I2 dash is the current seen by the source connected at the primary side. You are connecting the load at the secondary side. There is going to be some current in the secondary side, that is I2. But your supply is not seeing it I2, it is seeing it I2 dash. That we are calling as the current reflected. Load current reflected at the primary side. That is the important thing. I hope you are comfortable with this. I hope you all are comfortable with this. Now the most important thing, my dear friend, is to understand. The most important thing to understand here is what? That I wanted to tell you. That in case of load condition, what is going to be the flux here? There has to be some flux, yes or no? And what is that flux? This flux is going to be because of this MMF that we are calling as N1I naught. Are you getting this idea or not? Are you getting this concept or not? Please tell me quickly. Surya Saravanan is asking what will happen to the no load current when the load is connected. Beta, I am telling you what is your problem. Are you not getting it? This is the no load current. This is the no load current. This is the extra current drawn from the supply because of the closing of the switch S2. And this no load current is going to give you the MMF or the flux even at the load condition. I hope you are comfortable with this. I hope you are comfortable with this. This flux is going to be decided. This flux is going to be decided because of this MMF. See, if you have made your mind that whatever I am trying to say you are not going to understand it, then it is not my fault. Let me make it very clear. The way we are discussing transformer action, you go to any standard book, you will not find it easily. I am not saying that you will not find. You will find it, but not easily. The way we are discussing it. I hope it is enough for the transformer action. Now let us proceed. You all are comfortable with this transformer action? Can you tell me? If you tell this thing in UPSC Engineering Services examination interview, I can assure you that your examiner is going to get emotional after this answer if you tell him that how transformer action is going to happen. If you tell him this thing, he is going to be emotional. For very sure. Now let us proceed. And now we are going to see the EMF induced in the primary and secondary windings. I hope it is clear to all of you. Now let us see how we are going to find the EMF induced. Suppose this switch is closed, S1 is closed, suppose S2 is open. Because we are just interested in the EMF induced, we are not interested in the current at this time. We'll see the current when we will balance the MMF. When we will have the MMF balance, then we will discuss this switch S2 also closed. So let it be open. S2 is open. Okay. So there is going to be some polarity. Suppose at any point AC supply is there. And suppose there is going to be some EMF induced here as E1, and there is going to be some EMF induced here as E2. When this is positive, this is going to be positive. When this is positive, this is going to be positive. This is the transformer action and the related polarity that we have just discussed. And there is going to be some flux in this core. And suppose this is phi t. Now this phi t, I am saying that this flux is time varying flux. What is the meaning of time varying flux? It is going to be sinusoidal varying. So phi m sin omega t. Suppose this flux variation with the time is sinusoidal as we have assumed. Now if you apply the Faraday's law, what is the EMF induced in the primary winding? It is going to be N1 d phi t upon dt. Yes or no? Because N1 is the number of turns at the primary side and N2 is the number of turns at the secondary side. If you differentiate it, then you will get some equation E1 as N1 phi m omega, and sin omega t is going to be omega we have taken outside because of the differentiation. It is going to be cos omega t. If I ask you E1 as the RMS value of the EMF induced in the primary winding, then it is going to be how much? If this is the maximum peak value, so this is going to be N1 phi m upon omega divided by root 2. What is this omega? This omega is 2 pi f. If you put the value, then you will get E1 as root 2 pi f, and this is going to be phi m, and this is going to be N1. This is very, very important. You all must be knowing this, but the most remarkable feature in this equation is this flux. Here phi m is the maximum value of the flux. Are you getting this? Are you getting this? Now some students were asking me, sir, why flux is constant? When the load is connected, why flux is going to be constant? Now your answer lies here. Can you tell me what is this flux phi m? Can you tell me what is this flux phi m? It is going to be how much? It is going to be E1 divided by root 2 pi f N1. This is simple equation. No approximation, direct equation. Now you tell me, this E1 is going to be constant, root 2 is going to be constant, pi is constant, f is constant, N1 is constant. How this phi m is going to change? This phi m cannot change. And if the phi m cannot change, that extra MMF has to be compensated by drawing some more current from the primary winding. I hope it is clear to all of you. Now let us see the EMF induced in the secondary winding. The same theory we are going to apply here for the secondary side. Suppose E2 is the EMF induced in the secondary winding, so it is going to be how much? N2 d phi t upon dt. Again it is going to be how much? E2 is equal to, it is going to be N2 phi m omega, and this is going to be cos omega t. And if I ask you the RMS value of the EMF induced, then it is going to be N2 phi m omega upon root 2. Maximum value upon root 2, that is the RMS value for a sinusoidal varying quantity. Yes, Aditya Nanda, you can write 4.44 also, that is also correct, no problem. If you want to write 4.44, that is also correct. That is the approximate value if you see the root 2 pi, because pi value is not certain. Okay, exact value is not there, not possible. So similarly your E2 is going to be how much? Root 2 pi f phi m n2. Is it clear to all of you? Say this is equation number 2. What was equation number 1? Equation number 1 was E1 is equal to root 2 pi f phi m n1. This was the EMF induced at the primary side. Now we are going to know the secret why transformer is giving you the step up voltage. When I started teaching the transformer, I told you that no other practical device like transformer gives you step up voltage. You are connecting lower supply voltage at one winding, but at the load side you are getting more voltage. It is like a magic. How you are getting it? What is the secret? The secret, my dear friend, lies in these two equations. I hope you can crack it. And that secret is, if you see, E1 upon N1 is equal to E2 upon N2. Can you see this? What is E1 upon N1? E1 upon N1 is going to be root 2 pi f phi m. Root 2 pi f phi m, everything is constant. Again E2 upon N2, root 2 pi f phi m, constant. And what is this? This is EMF induced per turn. See, Sanjay Banthu, listen to me, beta. This leading lagging we will consider when we will discuss the phasor diagram. We have not discussed the phasor diagram, yes or no? We have not discussed. Is it clear? And let me tell you that leading and lagging of this induced EMF with respect to flux, it depends on what is the convention you are having. I have already neglected the negative sign. I hope you are getting this idea. If you keep the negative sign, then your statement is going to be truth. If I neglect then you will get this equation. I hope it is clear to all of you. Just have little patience. We'll discuss all these things. Why you are so much worried? Are you in a hurry? Just have little patience and listen to me properly. So how you are getting this more and more voltage? The idea is you keep on adding number of turns and you are going to get more and more voltage. Ideally, you can get any voltage. Ideally, if you go to the ideal transformer case, whatever voltage you want at the load side, you can get it because EMF induced per turn. That is basically EMF induced in 1 turn. You keep on increasing the number of turns and more voltage you are going to get. That is the overall idea of the transformer action and how you are getting the step up voltage at the load side. That is about electrical engineering about the transformer. I hope you understand this. Ramanan is asking, sir, E is proportional to N. So, beta, what is the problem? Yes, you can say like that, beta. You can say like that. Just wait. You all are very good students. Just have little patience. So, from here, beta, you can write. That E1 upon N1 is equal to E2 upon N2. Yes or no? Now please try to understand. If you talk about the ideal transformer, we'll consider ideal transformer also. If it is ideal transformer, there is no resistance involved and there is no leakage flux. So Rx or nothing is present. So whatever voltage is going to be applied here from the supply side, it is going to be equal to, I am taking the RMS value here. RMS value means the effective value. It means, and same is the case here because it is open circuit condition, S2 is open, and even if it is closed, please try to understand it is ideal transformer. So again Rx here also being neglected. So whatever EMF is going to be appear here, it is going to be the voltage across the terminals of the load. So very easily you can write, for an ideal transformer I am writing, for an ideal transformer you can write E1 is equal to V1 and E2 is equal to V2. If it is like that, then you can write V1 upon N1 is equal to V2 upon N2, or you can write V1 upon V2 is equal to N1 upon N2 is equal to transformation turns ratio A. This is very important equation. You must be knowing this. You must be knowing this. I hope it is clear to all of you. Now there is some important information regarding this Target GATE 2021, a course for GATE aspirants. Let us have some highlights of this Target GATE batch. This is very important. If you have not started the free trial, you should start the free trial. The scholarship test GEST is going to be held at 11th of May. That is very important. 5,000 plus practice questions. Study notes. Where do you get study notes? You are getting study notes also. You are getting full length mock test, daily test and subject wise test. You can say it is a comprehensive plan to ensure your success. I can tell you. Some more important dates, highlights about this Target GATE 2021. These are the important dates. The most important date is 11th of May, because GST is going to be conducted, so you can take a screenshot. Now let us try to discuss about the ideal transformer. All of you, please tell me, are you comfortable with this, whatever we have discussed now? And if you have any doubt, then you can ask me, otherwise I am going to proceed. Are you comfortable with this? All of you, please tell me yes or no in the comment section. Quickly tell me yes or no in the comment section. And repeatedly I am saying that you should like this page. If you don't like this page, how can we continue making these classes for you? It is very important that you show some thumbs up for our efforts. Even in these difficult times, we are working for you. So just show some like. That's it. That's all what is required. Okay. Okay, Sanjay Bontu is asking, sir, will you explain even polarity? Now let us go back and try to understand. Okay, let me use this figure. Okay, let us go back. Better to use this figure. Now see, Sanjay, please listen to me. Sanjay, please listen to me. Don't worry, I will tell you everything. Don't worry. But I am saying, beta, how you are going to decide the polarity of E1? If given an opportunity, suppose you are E1, you are standing here, you are E1, and you have been given an opportunity to flow current according to your choice. So what is going to happen? Because you have to flow the current as per your choice, I am going to remove this source. I am going to remove this source and I am going to place some load here. Yes or no? Now if the load is connected like this and E1 has to supply the current, in which direction he is going to supply the current? Opposite to the direction of current I1, yes or no? Are you getting this idea or not? This induced EMF, even given an opportunity, it is going to flow the current in the opposite direction that of I1, because it will oppose its own cause. What is the cause? The cause is I1. That is the idea. So what is going to be the polarity of E1? It is going to be beta like this, plus minus, because it is going to flow the current in this direction. And now are you getting? Please tell me. Sanjay, please tell me. You are my favorite student. You tell me. Are you getting now? Is it clear now? How to check the polarity, whether it is primary side or secondary side? I am again telling it. Given an opportunity to flow current of your choice, where you want to flow the current, That is going to be the polarity of the induced EMF E1 and E2, and both are going to follow the Lenz's law. That is how you can decide the polarity. Sanjay, I hope it is clear now. Let us proceed. Now please try to understand, for an ideal transformer, the most important thing that we are saying is, please try to understand, this mu r is going to be almost infinite, very, very high. That is the relative permeability. That is the relative permeability Ranjit Mahal is asking, sir, what is decided first for the design of the transformer? I don't know. I don't know, beta, what you are asking. I don't know, beta, what you are asking. Okay. Now please listen to me. We are saying that for ideal transformer, the relative permeability mu r is going to be infinite or very, very high. What is the reason? The reason is, if your mu r value is going to be very high, what is going to be? Please try to understand. What is your flux? Your flux is going to be MMF upon reluctance. Are you getting this or not? It is going to be MMF upon reluctance. What is MMF? Suppose at no load condition it is going to be N1 I naught, and even in load condition also, I told you, because of the transformer action, the MMF is going to be in the core. For this core flux, it is going to be N1 I naught, because whatever extra current you are extracting from the supply, that is just because you want to compensate the secondary current I2. I hope you are getting this. For the magnetization of the core, the current is again I naught, nothing else. Ranjit Mahal, beta, you have to wait. If you have already studied transformer from somewhere, I don't know, there are two ways in which you can see the Ramayana. Either you can see the Ramayana of the Ramanand Sagar, or you can see the Ramayana of Ekta Kapoor. Now it is your choice. I am not saying that I am Ramanand, neither I am saying I am Ekta Kapoor. It is your choice. For one student, I may be Ramanand Sagar. For one student, I may be Ekta Kapoor. So it is your choice. We are not discussing right now here the design of the transformer. We are discussing ideal transformer. If you are not comfortable with this, if you have studied it, beta, I can't help you. I hope you understand my point. Now I am going to write the reluctance. What is reluctance? The reluctance is going to be L upon mu A. A is the cross-sectional area, you can say. What is L? L is the length, you can say. Mean core length, you can say. Now from here, if you find the I naught value, the I naught value is going to be phi mu A upon N1. Now this mu is how much? This mu is mu naught mu R. Okay, just I think I have written it wrong. Just let me write it correctly. That is what happens if you keep on pushing me to the limits. This I naught is going to be how much? This is going to be phi into L upon mu naught mu R A, and this N1 is also going to be the denominator. Now if this mu R value we are saying infinite, if this mu R is infinite, this I naught is going to be how much? 0. This I naught is almost going to be 0. What is the idea? The idea is, for an ideal transformer, the flux in the core is set up without any magnetization current. No magnetization current is required to establish the flux in the core. This is the idea of an ideal transformer. I hope it is clear to all of you. And if it is so, please try to understand now. This switch is closed S1 and this switch is closed S2. For an ideal transformer, suppose this is N1, this is N2, R we are assuming 0, X we are assuming 0. This X actually represents leakage flux that we will discuss after that. Here also Rx we are assuming 0. I hope it is clear. So what is going to happen, please tell me. Can you write the MMF balance, yes or no? What is going to be MMF balance? N1 I1. Suppose at the primary side, what is the current? Primary side, the current is going to be I1. What is the current at the secondary side? Suppose this is I2. Suppose this is the dot here, current entering. This is the dot here, current leaving. So if you write N1 I1 and this should be minus N2 I2, yes or no? Do you remember the Ampere circuital law? This has to be H dot dl. Do you remember this? When we were discussing the magnetic circuits, then we discussed this. This MMF total current is going to be how much? H dot dl for this closed contour across this core. And what is this H? H is going to be B upon mu naught mu r. But this mu r we are saying is infinity, very high. So this H is going to be how much? Almost 0, you can say. If H is 0, so this is going to be 0 beta. So you can write N1 I1 is equal to N2 I2, or you can write I1 upon I2 is equal to N2 upon N1, which is 1 by A. This we are writing for the ideal transformer. All of you, please tell me, are you comfortable with this? If you have any doubt, then you can ask me. Now this is the MMF balance equation, and what are the EMF induced? The EMF induced is going to be how much? Suppose this is we are writing as E1, this is we are writing as E1, and this is we are writing as E2. Okay. So how you are going to write? Suppose you want to draw the phasor diagram for the ideal transformer, so it is going to be how much? It is going to be something like this. Suppose it is something like this. So suppose this is your flux in the core phi, and suppose this is your V1 is equal to E1. For an ideal transformer, V1 and E1 are going to be same, and this is V2 is equal to E2, and this I naught component is almost 0, negligible. I hope you are getting this. I hope you are getting this. And let me write current I1 and I2. Suppose this is your current. This we are writing as I2, and this I2 upon A we are writing as I1. I hope it is clear to all of you. Suppose this is phi 1 and phi 2. That is the power factor angle at the primary and secondary side. All of you, please tell me, are you comfortable with this? Are you comfortable with this understanding of the ideal transformer? Please tell me quickly, all of you. All of you, please tell me quickly, are you comfortable with this understanding of ideal transformer or not? If you have any doubt, then you can ask me. Okay. Now I am going to discuss. Now, just here also, just one more important point I am going to write, that we are saying, let me remove my photograph so that you can see the content. We are saying this V1 upon V2 is equal to N1 upon N2, and this we are writing as A, and this we are writing as I2 upon I1. Suppose we are writing this with the complex conjugate, so that we can write V1 I1 complex conjugate is equal to V2 I2 complex conjugate. So this is going to be the primary side power, and this is going to be the secondary side power. So for the ideal transformer, this is going to be the case. I hope you all are comfortable with this. Yes or no? Now we are going to discuss the practical transformer. Now please focus here and listen to me, what is practical transformer. See, we are running short of time. So what I am going to do, I am going to conclude the class here. You just go with this, whatever we have discussed till now. You just go through this once again. All of you who are not comfortable, who are first time reading this much, so you just have a quick revision, and tomorrow we are going to start from the practical transformer. And let me tell you one thing, that because of some technical problems, some 1 or 2 sessions were cancelled. There was some issue with that, so we are little bit lagging with this, whatever we have to complete. Suppose for example, today we were supposed to do the efficiency part, but don't worry, within this week, because we are having classes from Monday to Saturday, so within this week definitely we'll try to gear up, because this basic part is very, very important. We cannot miss this. So we are going to gear up with this, with our schedule or the lectures. So don't worry, just stay tuned to Gradeup, this platform, and tomorrow we are going to start with the practical transformer. Is it clear to all of you? Are you comfortable? No problem. And also one thing is more important, that in this online media it is very difficult to sit beyond 1 hour, and I don't want you to be peddled with this a lot of information. I want whatever you read it with all your calm composure, so that you keep it for your future. I hope it is clear. So there is no hurry. We are going to discuss the practical transformer tomorrow, and we will discuss the remaining topics also. Is it clear? So friends, I am going to conclude this class here. The remaining things we will see tomorrow. Let me give you about tomorrow's class, that we'll try to cover things tomorrow, and if things are complete, then we are going to start auto transformer tomorrow, and this is going to be very, very important. So don't forget to join me tomorrow 8:30 p.m. for machines class, and it is going to be really very, very important. These are the 60 plus Gradeup students who have made their name in the GATE 2020 toppers list. You could also be there if you prepare with 100% honesty and hard work. Your photograph may be there next year. So friends, thank you so much. I wish you all the best. Don't forget to join me tomorrow 8:30 p.m. Prep smart, score better, go Gradeup. Thank you so much.